Welcome back to Physics 141 Online. I'd like to work out a rather detailed homework problem which takes an ideal gas around a complete closed thermodynamic cycle where the gas begins at one point on a PV diagram and then goes around a cyclic process and ends up right where it started. And so part of the practice that helps us in solving problems like this is taking the given information, especially when it's just given to us in words, and illustrating the process on the pressure volume diagram, labeling it appropriately for the given information. So we see here that this is a diatomic ideal gas with a gamma value of 7/5. So we'll use that when it comes time to calculate the internal energy. And it's got a volume V1 expanding 80 isobarically at a pressure P1 from A to B. All right, so and then if I continue to read, it says it reaches 4 times its initial volume. Then the pressure decreases at constant volume from B to C, where it reaches a pressure P sub C. So what that means is somewhere we start off over here and we expand to the right at constant pressure and then go down in pressure at constant volume. So I will just draw on the diagram some initial point here, right? And then we're going to go over to the right at constant pressure. Boy, that's not very good constant pressure line. Let's try that again. That's a little better. Okay. And it says that it goes to 4 times its initial volume. So this is V1. And of course it says that the gas is initially at pressure P1. So this is point A right here. And I draw arrows to indicate which way the process is going. So from A to B, it's isobaric, constant pressure, and then it reaches a final volume, which is 4 times the initial volume, so 4 V1. Then, from point B, the pressure decreases at constant volume from B to C, where it just says it reaches a pressure P sub C. Okay, so we don't really know where that is, and once again, I'm having trouble drawing straight lines. We'll just stop it at here at some point. This is point C. Okay, that's the isovolumetric process where the pressure decreases. Then it says it's compressed, which means volume goes down, from C back to A, and it does so isothermally. And you remember how isotherms look on a PV diagram. They have this hyperbolic kind of character, and so if I draw that in, I put the arrow appropriately to show going from C to A, and that's my isotherm. So now we've taken the given information and translated that into a diagram, and one more thing I need to do is label this final pressure, the pressure at point C, and we'll just call it P sub C. So what are we trying to find? First of all, find the pressure at point C, which is P sub C, in terms of the given quantities P1 and V1. Then we're going to look at all the steps in the process and find for each of them the change in the internal energy, the heat absorbed, and the work done on the gas. And all the answers should be in terms of P1 and V1. So first of all, I'll just call this part A, and that's going to be to find P sub C. Okay, now the key to being able to figure that out, because we'd like to know it in terms of P1, it's probably going to be simply some fraction of P1, but what fraction is it? Is it 1/3 P1? Is it 1/2 P1? We just don't know until we consider that A to C, or sorry, C to A, that process is isothermal. So TA and TC are the same. TC equals TA. All right, so since we want to find the pressure at point C, we know the pressure at point A, so let's use the ideal gas law and this relationship, the isothermal relationship between the temperatures. So from the ideal gas law, we can solve for T. PV equals nRT, right? So T from the ideal gas law is equal to PV over nR. So with knowing that the temperatures are the same, let's just write this down. So PC VC over nR equals PA VA over nR. And I know that because that's simply taking this relationship for the temperatures and substituting in for temperature. So if I multiply both sides by nr, those drop out, and I find very easily, solving for PC, that PC is equal to PA VA over VC. And now let's look at the diagram. PA is P1, VA is V1, VC is 4V1, right? 4V1. And so we find that PC is equal to P1 over 4. And actually, my sketch is pretty close to that. It looks kind of like that PC could be a quarter of the way up to P1 at point A. So that's part A. Part B now is the meat of the problem, which is to find all these quantities. Delta U, right? Internal energy change is delta U. Heat absorbed, that's Q. Work done, that's W. And we want to find all three of those for each step, A to B, B to C, and finally C to A. And I said in class that it's always a good idea to make a table here. All right, so let's do this. Let's have one column for the step, and then we'll have delta U, we'll have Q, and we'll have W for each of these steps. Okay, so let's just see, there are three steps. There's A to B, then there's B to C, and finally C back to A. So there are 9 quantities that we want to fill out this table, fill out in this table in order to give us the answers for each step. And it's pretty clear that we're going to use the first law of thermodynamics to do this, because if we can find 2 of the 3, remember, delta U is always Q plus W for a gas. So let's see if there are any of these that are easy. And usually in processes like that, we can sometimes find some easy things. For example, look at step B to C. The volume doesn't change when you go from B to C, and since the work done, remember, work done is minus the integral P dV, right, from V initial to V final, and what that really means is it's the area under the pressure volume curve between the initial and final volumes. Well, if volume doesn't change, then work BC is equal to 0. So we know one of those. Now let's look at C to A. C to A is an isothermal step. And remember, delta U always depends on delta T. And for a diatomic ideal gas, if you look at the expression in our book, you see that this can be written as R over gamma minus 1 times N delta T. All right? The value here then of gamma is the one that will tell us what the coefficient out in front of the gas constant R is. So gamma is 7/5. So for this diatomic gas, let's see, 7/5 minus 1 would be 2/5, so we get 5/2 when we bring it up to the numerator. 5/2 NR delta T. That's for diatomic gas. That's for this problem. Well, if the temperature is not changing when you go from A to C, then delta T is equal to 0. So from A to C or C to A, delta U is equal to 0. So we have 2 of these 9 quantities already knocked out very easily. So let's now look at step AB. Is there something easy to solve for in step AB? And the answer is yes, the area. The area underneath that curve, right, when we go from A to B, if we just drop down a dotted line, the total area underneath that curve from the line AB down to the V axis is the work, although there's a minus sign, right? So work AB is, because it's an expansion process, the work done on the gas is negative, so it's minus P1 times V final, 4V1, minus V initial, which is V1, and so we get negative 3 P1 V1. That's our work AB. So minus 3 P1 V1. All right, we're on a roll now. How about for step A to B, let's look at delta U. Delta U, A to B, we now know how to write this down. For this diatomic gas, it's 5/2 NR times delta t, right, which is TB, the final, minus TA. What do I do with this? Well, once again, I'm going to use the ideal gas law. See, T is PV over NR. So let me substitute in this expression. So this gives me 5/2 NR. TB will be PB VB, right, over NR. And then we have PA VA over NR. And the great thing about making this substitution is the NR terms drop out. If I multiply through the NR that's outside the parentheses, it will cancel each of these terms in the denominator. So we can now get our answer for delta U AB. It's 5/2, and what we've got in parentheses is PB VB. So PB is P1, VB is 4V1. Then we subtract off PA, VA. Well, PA is P1, VA is V1. So it's just P1, V1. So 4 P1, V1 minus P1, V1 is 3 P1, V1. 3 times 5/2 is 15/2. So we get 15 over 2 P1, V1. So that goes right in here. 15/2 P1, V1. And once we have 2 of the 3 quantities, we get the third one from the first law. So let me just go over here and highlight that again. Right, in this case, now I know delta U and I know W, so I'll solve for Q. So QAB from the first law, solving for Q, is delta UAB minus WAB. And we're ready to plug in for this. Delta UAB is the 15/2 P1 V1. WAB is negative, so minus the negative is positive, so it's actually plus 3 P1 V1, and 3 is the same as 6/2. 6 plus 15 is 21, so I get 21/2 P1 V1. So I can plug that in here. 21 over 2 P1 V1. All right, so we now have A to B completely done. Let's move on to B to C. B to C, the nice thing is we have the work already. There's no simple equation for Q, so let's solve for delta U. And this won't be too difficult. We'll use pretty much the same strategy that we just used for step AB. So delta U BC, copying down the same basic equation, is 5/2 NR times the final temperature TC minus the initial temperature TB. Substituting for the temperatures, just like I did for delta UAB, gives 5/2 NR PCVC over NR minus PBVB over NR. The NR's cancel once again, and now we look back at our sketch, PCVC. All right, if we look at that, we can see it right here. PC is just PC, which is P1 over 4. VC is 4V1. So this becomes 5/2 times, what did I say it was? P1 over 4 times 4V1. That's the PCVC. Minus PBVB. So here I'm going to go back up to see the sketch a little more clearly. PBVB, that's going to be P1 times 4V1. Right? So I can, that makes it P1 times 4V1. Okay, what does that do? Well, the 4's over here cancel, and so we have P1V1 minus 4P1V1, which is negative 3P1V1. Negative 3 times 15 times 5 is negative 15, so we get negative 15/2 P1V1 for delta UBC. So negative 15/2 P1V1. All right, work is 0. The delta UBC is given, and now we go back to the first law and solve for Q. So QBC is just, right, delta U BC minus work BC. Well, work BC for this special case is 0, so QBC is just delta UBC, so we just copy it down. Negative 15 halves P1 V1. All right, only two left. Delta U for Ca, we know that already. Let's do work for Ca. And remember, Ca is an isothermal process, and we have a formula that I don't have written down here yet, but I'll write it down in a moment, that shows us how to find the work done, how to find the area under the curve when we go from C to A, and we know that it's an isothermal process. So what's that look like? You probably remember this, having seen it somewhere before, so we're looking at WCA, and for isothermal it's minus nRT. Right? I could write this as Tc or Ta, it doesn't matter because the temperature stays constant. And then it's the log of the final volume minus over the initial volume. So it would be Vc, since that's the final, over Va. Okay, so let's go back to our sketch. R times Tc, well, that's going to be, or Nr times Tc, that's just going to be PV for point C, right? So I can make this minus, using ideal gas law, minus PC Vc, which is just this whole term out in front, times now the log, and let's look at the sketch again, Vc over Va. Well, Vc, that is the higher volume, 4V1. Va is V1, right? So, oh, except I wrote it wrong, didn't I? All right, here's where I have to be careful. It's really easy to make these kind of mistakes. I didn't get the final and the initial right. Work Ca means we're going from C to A. See, so the final value for the volume would actually be Va, not Vc, as I'd written it. So let's fix it. Va is the final, Vc is the initial. So here we have the log of, well, Va is V1, and Vc is 4V1, so this gives us a log of 1/4, because the V terms cancel out. That's our work Ca. So let's take a look. Pc, we know what Pc is, that's P1 over 4, and Vc is 4V1. So I'll plug those numbers in right here. Looks like I'm going to need some space. So let me grab some space here by erasing some of the stuff that we've already done. Matter of fact, I think I can do maybe a better job of erasing it with a stronger eraser on my sketch pad. Alright, so that gives us a little bit of space. So this is negative. Pc, I said, was P1 over 4. Vc is 4V1. So the 4 and the 1/4 cancel, and we get log of 1/4. So the 4's drop out, giving a P1 V1 out in front. And here, what's kind of neat is that you can, if you have minus a logarithm, it's the same as having that logarithm to the -1 power. And so minus the log of 1/4 is the same as the log of 4 over 1. And so what this is, when the smoke clears, the minus sign goes away, the log becomes log of 4, so this becomes P1 V1 natural log of 4. And I won't plug the numbers in, I'll just leave it like that. So this is work Ca. Work Ca then is P1 V1 ln of 4. Sorry about that, it's kind of small, but you get the idea. And look, we can already just write down Q, because we know Q plus W is delta U, and for this isothermal process, delta U is 0. So Q is equal to minus W, so this becomes minus P1 V1 natural log of 4. And we're done. One thing that we can do to check our work, because this is a cyclic process, we know in a cyclic process we come back, as the word cycle implies, we come back to our starting point. So for the entire process, A to B, B to C, C to A, the delta U for that whole process should be 0, because we come back to the state at the same temperature that we began at. Delta U depends on delta T, so for the whole process, adding up the delta U terms should give us 0. And we can see right away that it does, because A to B has delta U of 15 halves P1 V1, B to C has just the opposite of that, C to A has 0, so add those three up and we get 0. So that checks out. That's something that we can often use in order to test to see if our results make sense. So I will end there, but this gives some pretty good illustration of how to tackle a problem like this where we're not given too many numbers, but we need to first draw the PV diagram and then use a combination of the ideal gas law and the first law of thermodynamics in order to fill in the thermodynamic values for the different steps of the process. I hope this helps you with the homework, and I'll see you in class.